In the previous video, we used Euler's formula to write down a new expression for the discrete time Fourier transform. And we tried to build intuition for this expression by thinking about the product of our data and sinusoids oscillating at different frequencies. In this video, we'll consider a simple example to try to make these ideas more concrete. Let's assume that our data x is a cosine function with frequency 10 Hz. Can we confirm through visual inspection that the signal x is in fact a 10 Hz oscillation? Well, one way to do so is to count the number of troughs that occur in this 1 second interval. If we do that, we find 10 troughs per second, corresponding to a frequency of 10 Hz. Of course, in real brain data, we would not expect to find a perfect 10 Hz cosine function, but this will be a good example for our illustrative purposes here. Now, what does our equation for the Fourier transform tell us to do? Well, it asks us to multiply our data x by cosine and sine functions oscillating at frequency fj. Let's start by choosing fj equal to 4 Hz. Choosing f sub j equals 4 Hz, we construct a sine and cosine function, each oscillating at 4 Hz. Then, to perform the calculation of our Fourier transform, we multiply our data x by the sinusoids at each point in time. Let's consider the product of our data x with the cosine function at 4 Hz. We show the results of this multiplication at each point in time in this lower figure. What we observe are some times where this product is positive and other times where this product is negative. Our equation for the Fourier transform instructs us to sum these products across all time. Doing so, we expect the positive and negative values to cancel and to find a value near zero. Repeating this analysis for the sine function, we'll find a similar result. We therefore conclude that both the real part, the cosine term, and the imaginary part, the sine term, are small. And therefore, big X sub j is approximately 0 when f sub j is equal to 4 Hz. Now, consider the case in which we choose f sub j equals 10 Hz. With this choice of f sub j, the data x and the cosine function align perfectly. The product of the cosine function and the data is always non-negative. And therefore, its summation over time results in a large positive number. In this case, the real part of big X sub j is large because the cosine function with frequency f sub j equals 10 Hz and the data x match. Repeating this analysis for the sine term, you'll find that it's near zero. In this way, the Fourier transform helps us identify the sinusoidal frequencies that best match our data.